Okay, in these next few videos, we're going to work on Chapter 3, Section 3, Polynomial and Synthetic Division. And what we're going to cover in here in the first two videos, we're going to use long division to divide polynomials by other polynomials. And I believe it's in the third video we will cover synthetic division to divide polynomials by binomials of this form. You know, some x minus some number. Again, that's called synthetic division. And we'll also cover in the last video, we'll talk about the remainder theorem and the factor theorem. Okay, over the course of this year and in previous years in math classes, you have done a lot with polynomials. You've added them and subtracted them and multiplied them, foiling them out. Division here is probably the least favorite of the operations with polynomials that I've found over the years. And just to refresh our memory about the division algorithm, I guess, the series of steps you use to divide numbers by numbers. So here we got 9,453, and we are going to divide that by 4. So we want to come up with a number here. What times 4 gets us closest to 9 without going over? Well, 2. 2 times 4 is 8. We write that under the 9 and we subtract. 9 minus 8 is 1. And then we bring down the next term, 14. Okay, how many times can we put 4 into 14 without going over? Well, 3 times. 3 times 4 is 12. Again, subtract. We have a 2. Bring down the next term, 5. We can put 4 into 25 6 times without going over, because 4 times 6 is 24. Subtract, we get a 1, bring down the 3, and we have another 3. 3 times 4 is 12. If we subtract 3 minus 2, we have a remainder of 1. And remember, we can take that remainder and make it a fraction. The remainder is the numerator of the fraction. The denominator is the divisor, 1/4. So what we just did here is found out how many times 4 can go into this number. Or another way to look at it is 4 times what we just found up here. If we multiply those, they will equal 9,453. So again, that's the division algorithm, or the pattern we use to divide a number into a larger number. We're going to do that with polynomials. So we'll have some x's and x squareds and other stuff in there. Let me grab this first. I know I'm going to need this graph here. Okay, so in this section, you're going to study two procedures for dividing polynomials. These procedures are especially valuable in factoring and finding the zeros of polynomial functions. To begin, suppose you're given the graph of this, 6x cubed minus 19x squared plus 16x minus 4. Before I even pull the graph up, it's a cubic and it's positive. So in the long run, it's going to go up to the right and down to the left. And these other terms, the minus 19x squared and the plus 16x, those are going to put maybe some twists around the origin. And this will be our our y-intercept at -4. So here's the graph. Again, in the long run, off to the right, we will go off to infinity. Here on the left, we will head down toward -infinity. And our x-intercept or y-intercept, it's just off the graph. It would be down here at -4. So it says, notice that a 0 occurs at x is 2. So here at 2, we cross the x-axis. Because x equals 2 is a 0 of function f, you know that x minus 2 is a factor of f of x. Remember, the last thing we do when we factor and solve things, we might have, we solve for x, we have x equals 2. Well, if I subtract 2 from each side, I get x minus 2 equals 0. And if I parenthesize it off, that is one of the factors of the polynomial. So we know that x minus 2 is a factor of the function f of x. This means that there exists a second-degree polynomial q of x such that f of x equals this factor x minus 2 times whatever q of x is. To find q of x, you can use long division, as we're going to see here in example 1. So example 1, divide this given polynomial, the big one, by x minus 2. Use the result to factor the polynomial completely. So I know that I'm going to, let me give myself a little more room. I'm probably going to need it here. I'm going to take this, and I'll write that out, 6x cubed minus 19x squared plus 16x minus 4. And I'm going to be dividing into that. And what I'm going to divide in there, I'll switch over to red here, x minus 2. X minus 2. So back to this real quick. Oop, I erased my just the numerical problem. We want to come up with a number up here And now, since we have two terms here, what we want to focus on is the leading term of each. This x and this 6x cubed. I want to come up with a number on top here. What times x is exactly 6x cubed? Well, I know I'm going to need a 6, and something times x is x cubed. Well, that something has got to be an x squared. And notice I did write it right over this x squared, which isn't too big of a deal, but it's nice to keep everything in order. So now if I multiply, 6x squared times this x is 6x cubed. And that's not a very good 3. Barely any better. But this 6x cubed times the minus 2 becomes a minus 12x squared. Now, most people, if they're going to make a mistake, they're going to make it here in the subtraction part. Remember, this is always subtracting just like it was, when we were just dealing with numbers. So 6x cubed minus 6x cubed is 0, and we always want that to happen. That's why we chose 6x cubed. Now we have negative 19x squared minus a negative 12x squared. So we add the opposite, and this becomes a plus. So that will be a minus 7x squared. And we bring down the next term, 16x, positive. So now we need something here. Times x is minus 7x squared. Well, that's got to be a minus 7x. Minus 7x times x is minus 7x squared. And minus 7x times minus 2 is going to turn into a positive 14x. Again, remember we are subtracting. Negative 7 minus a negative would turn that to a plus, and that term is now gone. 16x minus 14x is 2x. And we bring down the next term, and that's a minus 4. Okay, concentrating on the leading terms again. What times x is 2x? Well, that's easy. That's just a plus 2. So 2 times x is 2x, and 2 times minus 2 is minus 4. And look at that, the terms match up perfectly. When I subtract here, I'll get a 0 and a 0, so we have no remainder. So let me just, well, I guess I can erase everything below. Get rid of this here. All right, so what did we just figure out? Well, we knew we had the factor x minus 2. That was our divisor. And when we divided into the bigger polynomial 6x cubed minus, and all this other stuff, we found out that 6x squared minus 7x plus 2 had no remainder, so we know that is the other factor. Now, the direction said use this result to factor the polynomial completely. So that means, we have this x minus 2 factor. That still isn't going anywhere. But what we have here, this trinomial, this quadratic, our squared, x, and constant term, we can factor that farther. And again, they were trying to give us the hint from the graph that, or from the beginning of the graph, we know there's going to be two other intercepts there, and they're real tight, and they're both in between 0 and 1. So we know this is going to factor down again nicely. And through a little trial and error, there are several factors of 6. It'd be 6 and 1 or 2 and 3. It is going to break down into a 2x and a 3x. And then we need the factors of 2 that when we FOIL it all out, we will get a minus 7x in the middle. And that turns out to be a 2x minus 1. Oop, and why do I have that minus in there with that 3? That's not supposed to be there. Oh, that was supposed to be an x. So we got our 2x minus 1 and 3x minus 2. So there's the complete factorization, and what really gave us a hand was knowing x minus 2 was a factor. So we divided it into the polynomial we had, and that made it easier to factor this portion of it down. And to complete it off, if we set each of these equal to 0, we would have x minus 2 is 0. Add 2 to both sides, x is 2. That was the 1, 0 we already saw on the graph. If we take this one and set it equal to 0, we'll add 1 to both sides and divide by 2. So here we'll have x equals positive a half. And this one, this is a minus 2. We would add that to the other side and get 3x equals 2 and then divide by 3. So x is going to equal 2/3. And again, that is backed up graphically there. We can see here our polynomial makes a quick leap over the x-axis real quick. It crosses at 1/2 and goes positive. Then it crosses again at 2/3 and goes back down here into the fourth quadrant. And again, crosses for the last time here at x is positive 2. Wasn't that fun? Okay. Here's another example using long division of polynomials. This one's a little shorter. Here we just have a squared term, an x term, and a 5, and we're just dividing it by that little binomial x plus 1. Well, let's get ready here. We got our x squared plus 3x plus 5. And we are going to divide into that x plus 1. So move that up out of the way there. And we need something up here. What times x is x squared? That's easy. X. X times x is x squared. And then our x times 1 is plus 1. Ooh, and look at that. We're going to put that plus 1 over here. Ooh, oh, what am I doing? X times 1 is x. Why didn't you stop me? You made me look like a fool. All right, so now we subtract. I have seen students do it this way before, too. You know, they put a set of parentheses around here. And instead of writing the x up here, or maybe they just imagine it right here where they are going to distribute. X times x is x squared. X times 1 is x. So, you know, you could either do that visually or write it on your paper. You might have to erase it every time you do a term, though. But that might help not make little silly mistakes like I just did. All right, let's subtract. X squared minus x squared is nothing. 3x minus x is 2x. And we bring down the plus 5. So next we need a term up here. What times x is 2x? Well, that's going to be a plus 2. So 2 times x is 2x. And 2 times 1 is 2. So we got that plus 2. These subtract away. 5 minus 2 is 3. So that's our remainder. And again, we can take that remainder and make it the numerator of a fraction. So I'm going to come up here and make that 3 my numerator and my denominator x plus 1. And since that was a positive 3, I can put a plus sign right there. So what can we conclude from this? Well, we can say our original, x squared plus 3x plus 5, well, we can break that down. We can factor it. One of the factors is right here, x plus 1. And here's another factor, x plus 2. Oop, not plus, we're multiplying there. X plus 2. And then our remainder is a plus 3, so I could tack on the plus 3 here at the end. What? You don't believe that this times this plus this is equal to this? Well, let's just show that it does work. If we just concentrate here and FOIL, you know, first times first is x times x is x squared. Outer terms, here we would have a 2x, and in here a 1x. Well, 2x plus 1x is plus 3x. And then we have last times last. 1 times 2 is a plus 2. And then we could tack on our remainder at the end here, plus 3. Well, that adds up to 5. And this looks familiar, x squared plus 3x. So it does work out. So what we found is how to break this into its factors. X plus 1 and x plus 2 are 2 of the factors, and then we had the remainder of plus 3 at the end. And also, you know, this is another little interesting aspect on this. Let's say I asked you to factor x squared plus 3x plus 5. And, you know, in class, we'd set up some empty parentheses under here, and we'd know that the x squared is x times x, so that's easy to figure out. But then when we try to factor the 5, the factors of 5 are only 1 and 5, and there's no way to get those to go together to come up with a 3. Well, what we can do is take that 5 and bust it up. And we might say, okay, what would we want here to make this factor really nice? Well, what has the factors that would add up to 3? Well, 2, its factors are 2 and 1. So that would work real nice here. We would have a plus 2 and a plus 1. Well, if we broke up the 5, we had a 2 there. We would still have this leftover 3 piece that we would just tack on as a remainder. So there's our 2 factors multiplied and the little leftover remainder. Okay, and this leads to the division algorithm. So we have 2 functions. If f of x and d of x are polynomials such that d of x is not equal to 0, and the degree of d of x is less than or equal to the degree of f of x, then there exists unique polynomials, q of x and r of x, such that f of x, which is our dividend, divided by d of x, or f of x breaks up into d of x times q of x plus r of x. Now that's a lot of, you know, function notation right there, but just, you know, back that up and compare that to what we just did here. You know, this is our f of x. Here's our factor or our function x squared plus 3x plus 5. That would be f of x. Well, that's going to break into 2 things that are multiplied plus the little remainder. Well, oops, wrong way. Here are the two things that it breaks down into, plus the little remainder. Again, let me do this. So using this notation, we have d of x, q of x plus r of x. This would be d of x. This would be q of x. And this would be r of x, our remainder of the function. So if you multiply d times q and add r, that's equal to the original function. This would be our f of x. Again, that's a lot of notation there. Where r of x is equal to 0, or the degree of r of x is less than the degree of d of x, the divisor. If the remainder is 0, d of x divides evenly into f of x. Like this original one here, when we divided in, there was no remainder. There was no remainder in any of this. It divided out real nice. Where are we? The division algorithm can also be written as this. Let me erase this up here so we get a little better view of that. F of x divided by d of x. So if we take our dividend and divide it by the divisor, it's going to equal some other function q of x, maybe with a remainder. R of x is the remainder up top. D of x is just our divisor put down there as our denominator. In the division algorithm, the rational expression f of x divided by d of x is improper because the degree of f of x, the numerator, is greater than or equal to the degree of the denominator d of x. On the other hand, the rational expression r of x over d of x is proper because the degree of the numerator is going to be less than the degree of the denominator. Okay, a couple problems to practice on. This is the division problem. It's just written a little different. Write it out longwise and then divide in there. And, pause the video, give those a try, and then start the video back up and see if you got the answers right. Yeah, all right, let me get this one out of here for now. And we'll rewrite this one a little better for our long division. We are dividing x squared plus 2x minus 1 by our denominator, x plus 3. Okay, let's see how this works out. So we need something up here. What times x is x squared? That's easy. That's just x. So we're going to distribute. X times x is x squared. X times the plus 3 is plus 3x. And remember, here we are subtracting. If you want to, you could parenthesize that off, put a minus there, and imagine you distribute the minus, so this will become a minus. X squared minus x squared is nothing. This will also become a minus. 2x minus 3x is minus 1x. Okay, we want something up here. What times x is minus 1x? Well, that's got to be a minus 1. Minus 1 and x is minus 1x. And I forgot to bring down my next term, the minus 1. Minus 1 times 3 is minus 3. Again, we are subtracting. So we're going to add the opposite. So that'll turn into a 0x. And then minus 1 and plus 3 is a 2. So we have a remainder of a positive 2. So that's going to become a plus remainder 2 over top of divisor x plus 3. Oop, that is a 3. And again, that is saying if we multiply x plus 3 times this x minus 1 and FOIL it out, and then tack on a plus 2, we'll get right back to here, right back to where we started. Okay, that was an easy one. Next one's a little bigger. And again, it's written a little different than the first one was, but that's not bad. Here we have our x cubed. Ooh, let me move that over just a little bit. X cubed plus 4x squared minus 3x minus 12. And we're going to divide into that x minus 3. This one's a little bigger, but nothing we can't handle. So something up here times x is x cubed. Well, that has to be x squared. So x squared and x is x cubed, just like we needed. X squared times minus 3 is minus 3x squared. And remember, we're subtracting. These will subtract to nothing. 4 minus a negative 3, that'll turn into a plus, and that will be a 7x squared. So what times x is 7x squared? That's got to be a plus 7x. So we multiply those. Oops, forgot to bring down my minus 3x. So 7x times x is 7x squared. 7x times minus 3 is minus 21x. So we subtract. 7 minus 7 is nothing. Negative 3 minus a negative 21, that'll turn into a plus, and that winds up being an 18x. Bring down the next term, minus 12. So what times x is 18x? Got to be an 18. 18 times x is 18x. 18 times minus 3 is minus 54. Again, we are subtracting. Subtract here, that'll be 0. Add the opposite here. 54 minus 12 is 42. So that's our remainder. It's a positive 42, so we would write plus 42 over the quantity x minus 3. And again, if you don't believe that, or if you want to check your work, you could do it. Multiply x minus 3 times this, and after well, you wouldn't FOIL it because you got a trinomial here, but after you work that all out, tack on a 42 at the end, and those constants will all add up to this minus 12. And I think that's it for the first video. We got a worksheet, and if you're at home watching this because you didn't make it to class and you don't have the worksheet, I believe these here are the problems. So just copy those down on a piece of paper, and you can turn that in next time I see you.